All right, let's talk about routing. Now, you probably think of your GPS, or maybe how a customer service call gets to the right person. And you'd be right. But what's really mind blowing is how that exact same idea is now being used to build the actual brains of the next generation of AI. It's happening at two totally different scales, and it's a total game changer. So, yeah, let's dive in. So, to get our heads around AI routing, let's start with a really simple analogy. Imagine you've got a paper map. It's great, it's predictable, but if there's a sudden accident in a massive traffic jam, that map is completely useless, right? Now, think about your GPS app. It's alive. It's constantly analyzing live traffic, road closures, you name it, to find you the absolute best path, right this second. That leap from a static, fixed plan to a dynamic, real-time decision, that is the very heart of AI routing. So, okay, what is it really? Well, you can think of AI routing as a kind of smart decision layer that sits inside a system. Its whole job is to look at whatever is coming in, whether that's your call, a package, or just a piece of data, and send it to the most suitable destination. And the key word here is intelligently. This isn't just following a simple if-then checklist. It's using machine learning to make the optimal choice in that exact moment. To really nail this down, we've got to first understand that fundamental jump from the static, paper map way of thinking to the incredible power of what we call intelligent dispatch. And this is not just some abstract theory. It is already fundamentally changing how we interact with technology every single day. So let's pull this concept out of the clouds and see where it's already making smarter decisions all around us. You'll see the applications are literally everywhere, and often in places you probably wouldn't even think to look. Let's start with customer service. You know the old way, right? You call in, you get put in a line, and you just go to the next available agent. That's it. But AI routing, it's like a super intelligent matchmaker. It can analyze your specific problem and connect you with the one agent who has the absolute best track record for solving that exact issue. It can even, get this, detect frustration in your voice and pair you with an agent known for their empathy. Or it could identify a high-value customer and shoot them straight over to a retention specialist. You see the difference? It's optimizing for the best possible outcome, not just the next open line. And we see this exact same logic playing out in logistics and even in our computer networks. Delivery companies are using it to adjust driver routes on the fly, reacting to live traffic, bad weather, or even new orders that pop up. At the same time, the internet itself is a massive routing system. AI is proactively spotting network slowdowns and rerouting data packets in milliseconds, all to make sure your video call stays smooth. In every single one of these cases, it all comes back to dynamic, intelligent dispatch. Okay, so these examples show just how powerful routing is for dealing with tasks out in the real world. But now, here's where it gets really interesting. What happens when we turn this entire idea inward? It turns out that this same concept of intelligent dispatch holds the key to solving one of the biggest headaches in AI today, the scaling problem. The fact that just making an AI bigger doesn't always make it better. So here's the dilemma that everyone was facing. For a long time, the only way to make an AI model smarter was just to make it bigger, just keep adding more and more parameters. But the problem with these traditional, what we call dense models, is that every single parameter has to fire for every single calculation. So a smarter model meant a ridiculously huge exponential spike in the computational cost to run it. We measure that cost in flops. It was getting completely out of control, just way too expensive. And this dilemma led to a really brilliant question. What if we could take that same routing idea, that GPS logic, and apply it not to things in the outside world, but to the computation itself, deep inside the AI's own brain? Well, the answer to that question gave us a revolutionary new architecture called the Mixture of Experts, or MOE for short. And honestly, it's a fundamentally smarter way to build an AI, not with brute force, but with a kind of surgical precision. The secret sauce behind Mo is an idea called conditional computation, and it's actually a really simple but powerful concept. Instead of firing up the entire massive network for every single thought, the model learns to activate only the specific parts, these experts, that are perfectly suited for the task at hand. It's kind of like how you don't use your entire brain to tie your shoe. You just use the relevant bits. And that right there is the crucial difference. A dense model is a sledgehammer. It uses all of its power all the time for everything. It's brute force. A sparse MOE model, on the other hand, is a scalpel. It only activates a small select group of its parameters for any given input, which makes it incredibly efficient to run. So how does this actually work under the hood? Well, an MOE layer really has two main components. First, you've got a collection of these experts, which you can just think of as smaller, specialized neural networks. And then, and this is the important part, you have the gating network, also known as the router. This thing is the real brain of the operation. It's the component that looks at the incoming data and decides which of the experts gets the job. And the process the router follows is actually pretty logical. First, it looks at the input and gives every expert a score. Then, it turns those scores into probabilities, which is basically its confidence level for each expert's ability to handle this particular task. Third, it just picks the top few, say the top 2 experts with the highest scores. And finally, the answers from those chosen experts are blended together to create the final result. It's like a tiny, data-driven election happening billions of times a second. But, and there's always a but, this elegant new system introduces a brand new and pretty critical challenge. If that router isn't designed carefully, it can create all sorts of imbalances. And this is where we get into the art and science of load balancing. So here's the problem. The router can get a little lazy. It might discover a few popular experts that are pretty good at most things and just start sending them all the work. This creates huge computational bottlenecks. But even worse, it leaves all the other experts just sitting on the sidelines, completely undertrained and underutilized. All that potential capacity in the model just goes to waste. So how do you fix this? Well, there are 2 main ways people have tackled it. The classic approach is something called an auxiliary loss, which basically punishes the model during its training whenever it makes an unbalanced choice. It's reactive. But a newer, more clever solution is what's called loss-free balancing. This is proactive. It actually incentivizes the router to make balanced choices by making those overworked experts just a little less likely to get picked, encouraging it to spread the work around. Okay, so let's zoom out. When you put all these pieces together, the insane efficiency of MOE and the tricky challenge of load balancing, what does it all mean for the future of AI? Well, it points to a future that is way more specialized. We're shifting away from building single, giant, monolithic models and moving toward creating entire ecosystems of AIs. And this table here really just sums up the whole trade-off perfectly. Dense models are simpler, sure, but their computation cost is incredibly high. Sparse MOE models, on the other hand, have a really low computation cost for each token they process, making them super efficient when you scale them up. But, and here's the catch, they are way more complex and require a ton of memory, or VRAM, because you have to have all those experts loaded up and ready to go at a moment's notice. At the end of the day, it's an economic choice between compute and memory. And believe me, this isn't just some theory from a research paper. Mo is what's powering some of today's most powerful AI models. Just look at Mixtral. It has almost 47 billion total parameters, but for any given task, it only uses about 13 billion of them. Or look at Grok 1. It scales that up to over 300 billion total parameters. This split between total knowledge and active knowledge is fundamentally changing how we even think about what an AI is capable of. And that brings us to a really powerful line from the source material that just nails it. We are moving from building individual AI models to architecting systems of AI models, and routing serves as the essential connective tissue. That perfectly captures this massive paradigm shift. So, I'll leave you with this final thought. The rise of AI routing and these mixture of experts models, it poses a really fundamental question for the future. Are we trying to build one single, massive, all-knowing AI? Or are we actually in the business of architecting an entire economy of specialized intelligences, all working together? It's a fascinating question, and the answer is going to define the next decade of AI. Thanks for tuning in.